Anin, Bojo, Sarah Hazel Dijnikos, Nabizing Donjaba. Hello and welcome. My name is Sarah Hazel and I'm from Nipissing First Nation. I am the project manager for the Canadian Archaeological Association's Working Group on Unmarked Graves, and today I'm going to be talking to you about Resistivity Survey and our recommended data collection procedures for locating unmarked graves. I would just like to draw your attention to our online resources before we get started. We have two comprehensive guides, one technical and one non-technical. The non-technical is about investigation planning, and the technical one is about remote sensing. So if you go to this website, you will be able to access these resources. Unmarked graves investigations can bring up distressing content, and it is important to take care of yourself mentally and emotionally while doing this work. Please make sure you have health supports in place, or you can call one of the numbers listed on the slide if you are feeling triggered, and you can speak to a health professional. And I'll just leave this up for a moment in case you'd like to write one of these numbers down. Electrical resistivity techniques have long been used in archaeological and forensic contexts. Like other geophysical methods, this technique can produce both maps and profiles of an archaeological site, highlighting possible features or structures. It measures the ability of the Earth's near surface to resist an electrical current moving through it. A wide variety of instruments are available with different ways of conducting resistivity survey. However, the core principles remain the same. The method works by sending an electric current generated from a battery into the ground using metal electrodes. The computer measures the voltage between any two electrodes and then calculates the resistance between these two electrodes. Once a measurement has been made from the electrodes, the specialist interprets the shape, character, and depth of any observed anomalies and determines whether they can be related to a possible archaeological feature. The physical properties of the ground, such as soil type and composition, for example, sand, silt, or clay, porosity and ability to hold water, all affects the ground's ability to conduct an electrical current. The same is true for buried features such as walls and grave shafts. These will have different electrical properties depending on their physical composition. It does not matter if the resistance of the feature you are trying to identify, for instance a grave, is higher or lower than the soil surrounding it. It just needs to be different to be detectable. Resistivity survey has been used to locate graves in cemeteries. The technique is very good at identifying voids, which have high resistivity due to the presence of air, as well as changes in sediment compaction and moisture levels, indicating increasing or decreasing resistance. It is also well suited for high clay or conductive soils, environments that GPR often finds challenging. Like other geophysical techniques, it is important to remember that resistivity surveys locate changes in the physical properties of the subsurface that could be related to cultural or natural disturbance events, and not the objects themselves, like human remains. Therefore, interpreting this type of data requires caution, discretion, and expertise. There are two main types of resistivity survey. The first kind is called an area survey that maps a large area with a focus on a particular depth range. The second is called electrical resistivity tomography, or ERT, that images a vertical transect through the earth along a profile. Both methods have advantages and disadvantages, and the cost and/or time required can be different. Area surveys are conducted with a variety of instruments, including frames with variable probe arrays that are moved by hand, or electrode cart systems with fixed electrode widths. Such devices cover large areas quickly, and although they produce large area maps, they have limited ability to document variation in subsurface properties across a range of depths. In contrast, ERT systems take longer and are more stationary. They require the operator to place a line or grid of metal electrodes and allow the computer to calculate the ground resistance over a period of time. Once the calculations are done, the electrodes are removed from the ground and planted at the next survey location, which can be done in a grid with consistent intervals. While relatively slow, ERT can produce both maps of sites and detailed profiles of the subsurface with variable depths and resolutions depending on the electrode spacing. Both techniques have the potential to identify graves under reasonable conditions. When planning for a resistivity survey, it is important to remember that the depth and resolution of the data collected is determined by the spacing of the electrodes. The more widely spaced the electrodes, the deeper the electric current can propagate through the subsurface. However, widely spaced electrodes result in lower spatial resolution. The maximum data resolution is directly equivalent to the minimum electrode spacing. For ERT surveys, widely spaced electrodes also result in more area being covered per line, possibly decreasing the time necessary to survey a site. Additionally, there are different electrode configurations, which electrodes are sending and receiving the current, that will result in different types of data collected. As a result of all of these factors, many authors recommend shorter electrode spacing, around 25 centimeters, to get as clear and detailed a profile or map of potential graves and grave shafts as possible. Regardless of the variation in data collection, how you design your survey will depend largely on the equipment you have available. It is also important to remember that resistivity is helpful in cases where other geophysical techniques, such as GPR, fail. Notably, resistivity is a reliable technique in high clay or saline environments and in areas with lots of obstructions and vegetation, which environments that are typically prohibit the use of GPR. Data collecting protocols will vary significantly depending on the methodology and instrument used. In ERT surveys, electrode placement and how the current is transmitted between them has a significant impact on the resolution and sensitivity of the data collected. Common electrode configurations or geometries include Wenner, Schlumberger, pole-dipole, dipole-dipole, pole-pole, and gradient. For ERT surveys, multiple electrodes are set up in an equidistant straight line across the ground. Often these are centered above the area or feature of interest. Depending on how many electrodes you have available, it is best to place them at either 25 centimeters apart, which is ideal, or 50 centimeters apart, which is an acceptable interval. Each of the electrodes is connected to a cable that connects to the resistivity meter. The meter is pre-programmed with different electrode arrays that run resistivity tests between the electrodes. It's important that the cables, electrodes, and meter are not touched or changed until it has finished its calculations. You may need to improve the initial contact resistance between the electrode and the ground by moistening the insertion point around your electrodes with water. You can also collect 3D resistivity data by spacing electrodes in a grid pattern or collecting individual resistivity lines in a grid pattern. This is done much the same way you collect individual profiles. After you collect an individual line, you manually move each electrode a specified distance to the next profile. This is a time-consuming process, and again, it is best to limit the space between your profiles. Under optimal conditions, if you spaced each electrode 25 centimeters apart and each profile 25 centimeters apart, you will collect very high resolution data that could be used to identify potential graves. However, given that often it's only possible to get a few profiles done in a day, you may wish to increase the distance to 50 centimeters or a meter. However, this will decrease the resolution and possibly overlook graves. For area surveys, grids are established over the area of investigation in much the same way as for GPR survey. For the GeoScan RM15, 2 pairs of probes are used, usually configured in a twin probe array. The first mobile pair of probes are attached to a frame and are moved systematically across a survey area. Also connected to the frame by a 50-meter cable is a second remote pair of probes that are left in a stationary position to record background resistance. Data points are collected by inserting probes into the ground at regular points along transects marked by tapes. To identify graves, we recommend taking readings every 25 centimeters along transverses spaced 25 centimeters apart. Transects can be walked bidirectionally, like a zigzag, if the instrument is left in the same orientation. This shortens the time needed to survey, though it is still relatively slow compared to other techniques. We estimate that it takes approximately 2 hours to survey a 20 meter by 20 meter or 400 meter square area at this resolution. This process can be speeded up by connecting more probes to the mobile frame, though the resulting instrument is often clumsy to use and only works in ideal field conditions. Once the resistivity survey is complete, the data needs to be processed in computer software that generates plots and profiles for interpretation and presentation. File outputs are often XYZ files in ASCII format. Like other geophysical techniques, data processing is usually undertaken to reduce noise or interference and improve interpretability. Data can be presented and processed in 1D, 2D, or 3D forms. To transform resistivity data into 2D profiles and then plotted into 3D grids, the data must undergo a process called inversion. Most commercially available inversion software will automatically calculate the best resistivity model possible for the electrode configuration with minimal user input. Once this is done, processed resistivity data can be gridded and visualized in different software options, such as Surfer or a GIS. Resistivity survey data is often difficult to interpret. While more robust than other forms of geophysical data, it is often more challenging to interpret than GPR data. As a result, interpretations should be made by trained specialists, and step-by-step explanations of the different processes and logic models applied to the data should be outlined. Miigwech, and thank you for joining me for this module on resistivity survey. I have put the link at the top of this slide to our online resources for your convenience.